I want to welcome you to the Wulff Lecture, the Fall Wulff Lecture of 2024. I want to introduce Professor Allanore, our speaker today. I won't go on because, firstly, I'll not pronounce the French words in his CV. So let me make this brief. Professor Allanore earned degrees in chemical process engineering in France, was a research engineer at Archaeological, came to MIT as a postdoctoral researcher, I believe in that man's lab over there in 2010, and has been here on the faculty since 2012. Professor Allanore also, he is also the Heather Leckman Professor of Materials Science, Professor of Metallurgy, and also the Director of CAMRE, the Center for Materials Research in Archaeology and Ethnography. And what you need to know is that Professor Allanore is a world leader, maybe the world leader, in inventing low energy, low carbon ways to make things that we need in very large volumes, including steel, aluminum, and fertilizer. So before I hand over the mic, I do want to take a moment to acknowledge the name of this lecture. This is the Wulff Lecture. It honors the late Professor John Wulff. John Wulff taught in the Department of Metallurgy, then the Department of Material Science and Engineering for many decades. Among many other things he introduced, he created 3091, Introduction to Solid-State Chemistry, started teaching that course in 1968, and then gave the inaugural Wulff Lecture in 1977. I think I have a good picture here of Professor Wulff in action. And I guess that's probably, you probably know what classroom that is. I don't actually know, but the purpose of this lecture is to introduce a broad audience to material science and engineering, and particularly to get you excited about material science and engineering. So with that, Professor Allanore.
All right, thank you very much. Thank you. Thank you very much for the kind introduction. I'm going to dig right in, because if you came here today, you have read the flyer. Right? Do you remember that picture that is on the front page? So you're all curious about what this is about, and this is iron ore with the French accent. It's the source of iron and steel. Okay, you're gonna have to go home with this. It was formed about 2 billion years ago. Yeah, 2 billion years ago, and here I'm not the one doing the work. I'm not the one breaking the rocks, obviously, because I'm the one taking the picture. So I'm here taking a picture of this piece of iron ore in Brazil, made 2 billion years ago by our planet. And you can see the tiny particles of iron oxide. In that case, it's called hematite. Hematite, it's red, like in Greek. And it's made, this one is particularly made about 98% of iron and oxygen, right? So there's only 2% of things that are not iron and oxygen here. It's the quartz and in form of the silica that is here. And I made an effort. I brought back samples of these 2 billion years old rocks, which are the source of iron ore. So indeed, this is all about iron and oxygen. This is all about material science and engineering and processing. And if there is one thing you have to remember is that, yes, we always talk about the products, right? You always talk about the iron and steel bar, the car, I don't know, the conductor, you know, this stainless steel thing, or everything. Or you always think about the final thing that you guys are buying. But you need to remember that there's a whole side of material science and engineering which starts at the rock and the mining and the minerals. That's what allows you to then make the product. And I want to highlight that in material science and engineering, I think for the first time this year, we have an opportunity to send some of the sophomore to a mine. Yes, we are organizing the ability to send people. It might be in Finland, it might be in the south of the USA, it might be in Utah, it might be somewhere else. But we are trying to engage more in the practical world and send our undergraduate students to the real world, and that will include mining. Now, why do you care about this beyond, you know, your interest for rocks and natural materials? It's because your surrounding is made of steel. I've already made some analogy with you, the ramps that are here, the lamps. You know, there used to be a transformer here. Guess what it's made of? It's all about iron and steel, and you may see it actually. You may see it even when you come, you know, to campus, or maybe you go elsewhere, you travel. Everything around you is made either of iron and steel or with iron and steel. There is an understudied aspect of material science, which are the tools. If you've done any machining, you know that they are all made of iron and steel. So what is iron and steel? Steel are products that are made by at more 90% of iron Fe0. All right, so we already know that this is pretty remote from the iron oxide that I showed you at the beginning. Now, the kind of the situation you are in right now is the notion of modernity. You may have seen those curves before. This is showing you my lifetime, right? I was born around that time. And what happened during that time is basically the population has increased drastically. Now the scale is off. The scale is off here, but you may know that we might be 9 billion people in the next 40 years again. So the line is going to continue to increase. Now you may not know that the overall wealth of the planet has also non-linearly increased. And that's what I'm trying to show you here, is that there is much more wealth today for the newborn on average than what you would have 40 years ago. And that trend is expected to continue. If you continue to look at trades and economics, that's what will happen. But what is supporting that differential, right? What is supporting the fact that the 7 billion people now can access to modernity between quotes? Well, here it is. It's all supported by materials one way or another. At the bottom, you have the green one, which is biomass. You have coal, which is in gray. You have the minerals, which are the stone, the sand, the fertilizer, right? Everything that does agriculture, civil engineering, and so on and so forth. And then you have the metals at the end. Now, this is normalized by 1, okay? So they're all equal at a quarter, just because I need to do something with the math. So here is 4 billion tons of material total in 1980, and here is how it evolved. It was multiplied by 3x since 1980, and it's going to be multiplied by 2x again since 2060. There is no other way around this. There's no other way around this, just to be very fair. Now, what is interesting for at least my field is the fact that the share of minerals and metal is the one that is growing the fastest. Now, the scale here doesn't pay attention, but if you look at the real data, you will see that it's actually the one that is growing the fastest. So there is a link between this infrastructure, these features that you're all enjoying every day, your computer, the power generation, and all on and so forth, the batteries that you all love. All that thing is only possible because of these metals and minerals. And when it comes to iron and steel, it's particularly striking. So in 2023, about 1.9 billion tons of iron and steel were produced. Okay, 1 ton is 1,000 kilograms, it's 2,000 pounds. Right? So it's heavy, it's a big mass, let's put it this way. And you can see that there are no provinces on the planet where we don't at some point either make the iron ore or make the steel or consume the steel for doing something. This is very important when you do your hiking and all your things, you see the poles, how the towers are made. Well, the towers at some point, they have some iron and steel and some concrete. Anyway, the point here is, of course, there is a big, big, big circle here. The last 20 years have been defined by the growth of China, and that has led to new capacity. The state-of-the-art iron and steel making is found in China today because they are the ones who are the last who invested really in iron and steel production. And that's going to explain why half of it is made right now in China, mostly consumed in China, right? To make the products that we are all buying. So it's all fair and fine. The challenge that's going to happen, of course, is the future of demand is not going to be probably in China, but in Southeast Asia and the whole African continent in general. So there's going to need to be the more capacity, and guess where the more capacity will be deployed? Probably in those regions that need it the most. Now, the sustainability challenge, right? The balancing act of this problem is today, we emit 1.85 ton of CO2 per ton of steel that is made. So you multiply the number and you see the math. That material supply comes with an even greater mass of carbon dioxide. And in that case, these are almost entirely direct CO2 emission. It's directly CO2, as I will show you, coming out for the processing of the ore that is here on the table. Now, you may have seen we have an archaeology of materials program in material science and engineering, which allows you not only to apply the most rigorous material science and engineering to ancient technology and ancient materials and questions, but it also allows you to reflect a little bit about the humanities and where do we come from and how did people think about matter before and so on and so forth. And here it's shown on a pottery, right? That's usually the famous material for archaeology is potteries, ceramics. If you don't know why ceramics are still present nowadays, you'll take material science and engineering. You will learn everything about why is ceramics one of the last things we see when we're doing studies of, in that case, ancient Greek in 400 BC. Now you see your two favorite titans. Anybody follows the Greek mythology? Yeah. So these are not gods, huh? These are titans. There are two of them. One of them is Prometheus. The other one is Epithemius. Did you know what they did? They were, there's a version of it from Socrates and Plato, which is basically telling us that they were responsible for giving qualities to everything that was living on the earth. You remember the mythology, right? The gods, they had everything, they knew everything. But then under that, they were the mortals, you and me. As far as I know, you and me. But we are mortals, and once you've given properties of the bird can fly, right? We give wings to the birds. What's the other one? I don't know, maybe the tiger, right? Big teeth and huge paw and can go around. Some elephant, huge thing. So well, then they did that, and then they go through the list, and there's one left. The mortals, right? What are we going to give to the humans? They don't have any qualities. We don't have any physical quality compared to anything that nature does. So what did they do? They literally forgot, huh? You may remember that. What did they do? Well, they went and they stole. They stole the things that only the gods are allowed to do. The gods are allowed to do art, power, fire, poetry, thinking. And that's what you see here on that picture representing, I don't know which one is which. I think this is Hephaestus. Hephaestus is the god of blacksmithing and fire and so on and so forth. And on the other side, you have Athena. Maybe you remember Athena at MIT, right? That's a joke. Computer science, you're right, Athena cluster. They disappeared, they dissolved. Anyway, Athena. So here is Athena, he's taking the art, right? Mind and hands, right? This is all there, there's nothing. We didn't invent anything. But anyway, it's quite interesting because the gods were very angry, right? And they punished Prometheus. And us humans, we have a new quality. We have technique. We have technology, right? That's what this is about. But technology is both what allows us to survive, but it's also a drug, right? It's also an addiction, and you can use it in a manner that ultimately hurts us more than helping us. All right, enough with this. We'll go back to the pottery soon, but for now we have to go back even further in time. We have to look about physics. If you do material science and engineering, you will learn some interesting physics, not necessarily the physics that I'm going to talk about, but a physics that is quite universal. You may remember that the origin of this iron that is sitting on the table is from a star, a supernova. This is unbelievable. I'm touching iron that was made in a supernova in nucleosynthesis. And how does it happen? Well, the universe is made of hydrogen, helium, right? That's the primary source in which nuclei are merging. They merge. On the way, they generate huge amount of energy. That's a detail. For us, we just care about how the elements appear. Here they appear, and at the end, at some point, they reach the size of iron. Right, element 26, that's pretty much the point at which by fusion you're not going to fuse much more. That's how the density increases, and the core of this supernova contains the iron, which will create all the gravity and density we're going to think about. This is so important that even in 2012, the Harvard laboratory using the telescope was able to study Cassiopeia. It's far away, 11,000 light years. But still, you can see it in 2012. And what did you see? What did they do? They immediately analyzed if there was iron in it. Iron, silicon, all the elements that we're going to talk about in a couple of minutes, they are the one that dictates the story of the universe. Now, I know it's far away, and you're tired with these fancy particles. It's very complicated. I understand. But it's quite remarkable to notice that iron already in the universe has a role that is pivotal, right? Because after iron, the rest is a detail, right? The rest is fission, and sometimes it happens and they don't disappear. I mean, it's a random thing. But iron, you will see it. People date universe event based on how much iron they see, to tell you how iron is important. All right, so you got it. This is far away, not your concern. That might become your concern, right? I hear that some people are thinking, we're gonna colonize this place, right? This is the solar system. There's no more hydrogen, no more helium, all of that is gone. Yeah, there's no hydrogen. Yeah, I'm gonna repeat that often. Here it is, right? So here is Mars. You see it with your eyes tonight. Hopefully, you go outside, you raise your hand. No computer, nothing. You will see this looks red. It's red because of hematite, Fe2O3, the same red that is here. Now, in terms of chemistry, it's slightly more complicated. 3 atoms of oxygen, O2 minus. We call them oxide because of the oxide bond, right? Here is the oxide. And then the iron is no longer elemental. It's no longer a plasma. Right? It's condensed and it's cationic. It has lost 3 electrons. It's Fe3+. Now, however, why is it red? It is red because of the band gap, which is exactly what you will learn in material science and engineering. On the other side, you have firelight, which is sitting in olivine. I know it's not just firelight, whatever. It's basically an iron silicate where you can see the chemistry is drastically different. It's the same story, right? The surface is oxidized. There is the atmosphere that interacted, but now for reasons that are entirely material science, the iron is only 2+. It kept 1 electron. And here is no longer binding with oxygen, but binding with silicate. Now you're appearing a new molecule that is responsible for this, and without any surprise, perhaps because of the valency, perhaps because of the silicate, this is now 3 electron volt, which if you look at the spectrum, correspond pretty well to greenish. Now, magnetically, these are completely different. So here we are. Here we are able to understand things that are happening in the solar system using all the tools of material science and engineering, and perhaps inventing ways you could make oxygen on the moon. Because remember, there's no breathable oxygen there. How are we going to make the oxygen? Well, we're going to have to take it from there. Oh, on the way you make iron. So everything that I'm talking about is not just a thing that's going to happen in the next couple of weeks. It's something that's going to give you a trajectory forever. Well, now we are here, poor mortals on Earth. You may remember we still have the elemental iron that is here in the core, right? That's why we have the density. That's probably why we have the magnetic field. But as you get closer and closer to your surface, right, where humans can probe, you can see what's going on. Very interesting chemistry. More and more sulfur, more and more oxygen, and lighter elements are starting to interact with the iron and give you the mantle and the upper mantle. So we live now in the regions where most of the iron you find is oxidized, either oxidized as 3+ or 2+. Well, I go further than that to claim that if the universe is iron-based physics, somehow, the Earth chemistry is iron-based as well. Now, this is really important because we see that if we start with the same iron oxide that I showed you before, right, 3 plus O2 minus, what can it do? Well, it can release electrons, right? It can become 2+, but the only way it can do that if the oxygen is oxidized. This is the famous iron 3+, 2+ ratio, which if you go in any other field, civil engineering, soil science, all these questions, you will be always facing how does a natural system is able to bring oxygen and condense oxygen. You see that oxygen is condensing by that direction. It's going from a gas to a solid in that case, and on the other side it decondenses, I don't know, it becomes gas. So this is very important because people know nowadays that actually those rocks were made by the early phenomena that allow oxygen to be in our atmosphere. The breathing, in a sense, of those bacteria led to solubility or no solubility of iron 3+ and 2+, and therefore allow the precipitation of this. And on the side, the life of bacteria and life. This is as you may have guessed, this is the detail. Now, your molecule, if you do blood, if you want to transport oxygen in your system. It's also based on iron, which either is a coincidence or maybe there is something greater than that. The last aspect, which I won't mention before, comes back to the color. There are 16 versions of iron oxide, at least. So I'm showing 4 of them. By the way, we have samples at the end that you are not allowed to touch. But I'll stay around and I can talk about them if you want. So here it is, right? That's the first one, hematite. It's mostly an insulator. It has an hexagonal crystal structure. You can see that the crystal structure, you can, I say that every time, right? If you know about iron oxide, you know everything about crystal structure, like everything. Just let's do a crystal structure of iron class, and that will be done. Anyway, here it is, insulator with oxygen. It has a certain color, which depends, by the way, on the size of the particle. But you can see, you can have black ones like magnetite, which if you go to the beach or if you go into, places where you can, I don't know, enjoy your time, you can buy magnetite because it brings you, I don't know what it brings you, but they sell it. If you go at the beach, they sell you magnetite. It's an electrical conductor, by the way. Yeah, see the difference? There's only one atom difference, right? One is 2+, everything else is 3+, but that's sufficient to drastically change the conductivity property of your system and the magnetism. You go on and on, maybe you're more familiar with this one. If you do hiking in New England, you see that type of bogey iron, which is gray, yellow, or yellow-orange, which is present. All right, so let's look back a little bit at archaeology of materials, because as I said, there are interesting takeaways. So archaeology of materials is about using the tools of structure property to reconstruct maybe ancient technology and trying to understand how did people make these decisions. Because we always think, oh, in the past, they didn't know what they were doing, whatever, but I'm just showing you the color changes, the feeling changes, the heat conduction changes. You think these people didn't have fingers that were as efficient as yours? You think they didn't smell as good as you? You think they didn't hear? No, they were probably even greater than that because they didn't have all these artifacts that you guys are carrying with you to live. Huh? So here it is. Well, it's hard because every 20 years we discover later and later age, but let's say 1600 to 40 BC. You will agree with me, this is very early humans. They are so early that we don't call them humans, right? Hominids, I can't say it. Hominids, whatever. Hominids. Neanderthals was living in that region. Now we're finding it everywhere, but anyway. It was there, and what's important is we find caves, right? And in those caves, the only remains of those people live. Did they live in caves? No. We just find traces of their life in caves, right? Okay, I just want to make it clear. Maybe they were never in caves, just once in their life. But anyway, we see them, right? We see them. I hope you have a chance to see that. I think you can see a copy of it. Yeah, in the 20th century, we make copies of what early humans were making so that current humans can see them. And guess what they use to remake that? They use material science and engineering. They need to know what color to get, how does it stick to the wall, what does the carbon do, if I breathe, does it disappear? I mean, all these questions are center and core to this history. But you can see the color, right? These are all different types of iron oxides. How did they know? How did they figure out that if there was more 2+, it would achieve that? And how did they achieve more 2+? You think that they wander around this entire region to find iron 2+? I don't know. Maybe they had amazing animals to go very fast. I don't know. Very interesting. Now, occasionally, this happens, right? So I'm not very fair to say that we have no more iron. We have iron metallic that comes, it comes from meteorite. Oh yeah, the same place that I talked about before, right? It comes from far away. There are still some original meteorite, and you can see there are some very special solid state structure that you see in those meteorites. And that's actually how we know that even maybe 10,000 BC, 5,000 BC, there was some iron that was used by humans, but most likely by analyzing the structure, we can relate to the fact that it didn't come from reduction of iron oxide, but it came from the outer space. All right, so I'm not going to dig too much into this, but you have to realize that those potteries, right, beyond the beautiful titans, the potteries have colors. How can you achieve that type of resolution in a pot that is made with ceramics? So there's an entire science of fire technology, high temperature technology that apparently came along with the early humans and that has continued to be practiced, either strictly for pottery and sometimes a little bit for metallurgy. And it is believed that that's how at some point, for reasons that are not explained today, but in 3 weeks, we have a lecture from an archaeometallurgist who knows everything about early iron in Africa, because we believe that's probably in Africa that the very early one happens. Anyway, my point is the mastery of high temperature and ceramics and the refractory materials allowed ultimately to achieve to the conversion of the iron oxide to steel that I talked about. So here it is. Here it is now illustrated in the Middle Age in China, what is today China. And you can see that the technology is based on some kind of oxygen or air that is blown through a bellow. So this is like an accordion, right? This is basically pushing air into the system. And what I know it does is that it creates fire. Why do I know that? Just because I watched the picture, right? I see the flame or the fume coming at the top, and I'm like, I think they were doing a fire. Okay. Now, there's things that are poured away, right? You see there's a liquid coming out, and I know if you were doing this with water, you would not have flames, so something is going on. Now, this is the very early principles of iron and steel production. Here is the chemistry, the carbon, mostly from charcoal. All right, so wood that you partially burn, that gives you charcoal. This charcoal is very reactive, and now you can use it to blow more oxygen. If you do that, you're going to reach high temperature, and you can see that the carbon can combine with the oxygen and leave behind the iron, and immediately you relate to the 3.5 billion tons of CO2 because they directly come from this reaction. Now, in a modern way, perhaps treating iron ore or any types of natural mineral is about the reassembly of the atoms, right? Because what you're trying to do is really push away the oxygen and leave the iron rich behind. Now, how this is done? Well, you can think about this as being done as the oxide reacting with the carbon or the carbon monoxide, give you CO2, but now you're left behind with the excess electron, which then immediately are kind of taken back by the iron 3+ to become iron 0. Now, this is a modern view. It is quite clear that this is a way of thinking that you will see is very biased, because ultimately, if you think about electrons and atoms, it's much easier to think about materials than if we stick only to the molecules and the gas and so on and so forth. All right, so here we are. Here we are, the integrated steel plant of today. I think integrated, you understand. Steel, you understand. Plant, you may not. Because if I say plant, usually people think of green stuff. Now, a plant is because it's the place where we do things. That's where we're going to basically allow these things to happen. Nowadays, it's not much hotter, 1600 degrees Celsius, and it's done in these 3 furnaces that you see here. These are the blast furnace. Carbon is a reductant, right? It does the oxidation of the oxygen and the reduction of the iron, but it's also a fuel. It's the only source of heat that allows the reactor to achieve its temperature. Nowadays, we don't use only iron or carbon, we also add alloying elements, manganese, silicon, chromium. If you want to have oxidation resistance, you're going to have some chromium in this. Nickel, if you have even different type of shape. But what is remarkable with this is you can see it in the forefront of the picture is that that amount of liquid iron is actually transformed, alloyed, and then continuously cast. And it's solidified almost, after here it's now finally solidified, and then it will go, while it is still hot, at about 700 degrees Celsius, it will go to further heat treatment, and it will start to be deformed so that you can get a shape that is acceptable for your next customer, which might be the car industry, which wants to stamp it, which wants to cut it, bend it, and weld it. And in order to do that, you need to position the atom of iron, carbon, manganese, and others in the right position, in the right structure. Now, how this is done and how is it possible? It's thanks to the heat treatment, the rolling, and the high temperature operation directly from the liquid state. Now, this is very difficult to apprehend. There are about 300 of those plants in the world. Each of them make about 4 million tons of iron per year. This is very difficult to comprehend. So 4 million tons per year means that the volume of that room has been filled in 7 minutes of liquid iron at 1600 degrees Celsius. So I've talked already too long, but anyway, four times, right? So we've already filled up 4 times the volume of this with liquid iron, and it's going to go on like this for 10 years, every day, every minute. Scale, I don't know how to tell you scale. I can tell you 30 meter, 15 meter. So I found some kids, right? I said, hey, how about we put some kids on the planet? So here. This is a very tricky exercise. It took me a lot of time because it's a projection, right? This thing is about 1 kilometer long, right? So this is actually very far away. So here is this is a normal human, right? How do you know? Because there is a rail, right? This is the safest industry you will ever meet. I want to put this out there. This is the safest industry you've ever meet. When you see what they're doing, right? They're moving 4 million tons per year, and you see how many people are, of course, there are always accidents, it's terrible, but my point is that's the one that know that nobody wants to work there if it's risky. So there are handrails everywhere, and the first thing you know, did somebody work in an iron and steel industry here? Can you walk the stairs? How do you walk the stairs in the iron and steel industry? You remember that? Exactly, you hold the rail. You see how it's incredible. All right, another sense of scale. Here is your tiny guy sitting here, sitting here. That tells you a sense of scale. That's just one blast furnace. Huh? There are 3 of them. All right, so this is all based on carbon and oxygen, as I showed you with the chemistry. And what about the cost? That's the favorite part. Sometimes you complain. So here is a piece of iron. Steel, actually. This is a kilogram, 1 kilogram. You can see it after that, but not now, okay? Now, how does it cost? It's here, it's noisy. I'm gonna make it full, here it is. So I bought something you probably don't use anymore. It's called coins. They are not made of iron. So that's, I'm not from here, but that's a quarter, right? So here is a quarter. All right, so that's 25 cents. I don't yet have the whole rod. I need a nickel, 5 cents, right? So here it is. That's what the industry is paying to make that product. Now here it's molten, okay? It's not yet continuously cast. Oh, there must be much more money made on the continuous casting and the hot rolling and the physical metallurgy, all that stuff makes so much money. Okay, I give you this. 35 cents per kilogram. Okay, so let's think about decarbonizing that problem, right? What is the frontier? The frontier is how we're going to think differently about that problem, and that's what we want to do in some of my research activities. So let's go back to the fundamentals, right? I really love physics. I love everything that we do with electrons and atoms and quasi-particles. Oh, that's wonderful. But ultimately, you want the iron atoms, right? You really want the mass. You want to separate the oxygen from the iron. It's more as much a chemical problem as a physical problem. I mean, you could pump. If you take the class I teach 319, Sustainable Chemical Metallurgy, in the spring, I will show you how much you have to pump, vacuum, right? You could suck the oxygen out. You can do it. I mean, you can think of doing it. I think it's 10 minus 20 atmosphere. There needs to be nothing left until the oxygen wants to leave the system. That's why they're only in the universe that you find this thing, not on Earth. All right, anyway, so you would say, hey, come on, electricity is here. I didn't know when they chose the room. There's an original electrical meter, amperes and voltage. I'm like, this thing has been there forever. Electricity, the first battery made on metals, thank you, copper and zinc, right? Right, so what, 1800 Volta? Then Faraday used a disk and start to discover that rotating something electromagnetic, you can actually generate electricity. How did they do that? With magnetic materials. Which magnetic materials do they use? Iron and steel. Huh? There's no other material that you can have at large scale that's going to be good enough to actually generate friction. So the point is, electricity, once it became available, thanks to Faraday, Weston, Siemens, hydroelectricity, ultimately, everybody said, we're going to use it to make materials. That's the most obvious thing to do. It's modern, it's fast, you turn the knob, it comes in, you don't have to wait for the coal to come. I mean, it's wonderful. So here it is, right, in 1901, written by Émile Zola in a book called Work. I didn't choose the title. He did in 1901, Work. We're trying to do chemical separation and the name is called Work. Okay, here it is. I changed the name. So this described the life of a valley in the French mountains. And in that valley, there is one iron and steel plant, okay? And Zola, you may know, was a humanist, anarcho-syndicalist, you name them the way you want, doesn't matter. He was trying to describe the social life and the love affairs between the classes, the wealth classes, that were happening in that region. So the whole book is not that much about iron and steel, but there is a passage about it. So here is the excerpt, right? So I changed the name. Mr. Smelt is the owner of the steel plant. That makes sense, right? It's not because he's making fish. It's because a smelter is a place where we remove iron oxide to iron, right? So when you extract metals from ore, you call it a smelter. So Mr. Smelt, and then the other character is Mr. Coulomb. I hope that you know, you just look here, there's his name. No, not here, here. There's his name on the building, right? So if there's a name on the building at MIT, you have to learn about that name. Right? That's the obvious thing to do. Anyway, Coulomb you may know because that's the chart, right? Anyway, so Mr. Smelt, he felt that he was threatened. He was aware of the researches which Mr. Coulomb was making with the view of replacing the old snow barbarous smeltery by batteries of electrical furnaces. Émile Zola was a journalist. He was a writer. And look at the language that is chosen. I hope you appreciate the quality of the journalism back then. It's extremely precise, extremely accurate, and the rest is even more accurate. The idea that one might extinguish the pile that flamed for 7 or 8 years quite distracted the master smelter. However, at the cost price still remained too high for electricity to be employed. He was able to rejoice over the futility of Mr. Coulomb's victory. 1901. Who Zola is talking about? Do you think he's inventing this? No, this is happening, right? This is basically this person here, Héroux, who invented the electric arc furnace, which was deployed very early on in California. This is the city of Héroux-on-the-Pit, which doesn't exist anymore. But what's important to notice is that they are saying it, right? The price of electricity was just too high. However, electricity could be used for melting. Remelting scrap, you can see it here, that's the amount of energy consumption in the USA over the last 40 years. The USA is the most efficient iron and steel industry in terms of energy consumption, thanks to electricity and the electric arc furnace. And this was possible here because of the free spirit market of deploying new technology for making things as long as they make money. Now, Héroux and Hall simultaneously invented as well the aluminum electrolysis. We're getting closer here to the current research, right? Because you can see this is a carbon anode, you have the metal at the bottom, this is an electrolysis cell, and continuously the oxygen is removed by the CO2 at the anode, and then aluminum is made at the bottom. How is it done today? Here it is. These are the aluminum electrolysis cells, which make 60 million tons of steel per year. Again, you get the sense of scale. This is about a mile long, right? Almost a kilometer long. This is one cell about the size of a swimming pool, a small swimming pool. And these are the anodes, the liquid metal is at the bottom, and the electrolysis happens continuously. The gas is collected here and transferred elsewhere. If you just wanted to replicate that technology, ignoring everything, you would need to be 3 times faster in order to match the 1.9 billion tons per year. Second thing, you would have to reduce the amount of heat losses. Aluminum is made at 960 degrees Celsius, so they are okay with heat losses, and aluminum is a bit more expensive. Now, that's what we're trying to think about. How would you do electrowinning differently? How could you use directly electricity to do the decomposition of, let's say, a metal oxide? You would need an anode, a cathode. You evolve gas on one electrode, maybe oxygen, and at the bottom, you make iron metal. I know you all want to go into perhaps new ventures and startup and raising funds and all that stuff. You only need to know 2 things for electrochemistry. That's why we make so many startups. You need voltage, right? You need the cell voltage to basically do the chemical work, okay? How do you get that? It's mostly thermodynamic, a bit of irreversibility. If you know that, these are physical constants, don't worry about it. This is how efficient you are, and that gives you the number of kilowatt hour per ton, right? Gigajoule per ton that you would need. The second parameter, as I said, you need another one. It's called the current density. How many amperes can you flow per square meter or square feet of electrodes? Because electrochemistry is a surface-driven problem or phenomena, and therefore you need a maximum amount of current per square meter. All right, so here you are. You're ready to do your business plan. The problem, of course, is you have to do that in a manner that is informed by science and engineering, and that's what we do in material science. Now, this is a special breed of it, because in our case, this is molten, high temperature melts. The good news is that they are used in industry anyway, so you're learning things anyway. But for example, you would want to know how much can I dissolve iron oxide in that electrolyte. You would want to know the transport property. What is carrying the current? You know, is it the anion, the cation, which molecule, how fast can they move? And finally, you need a container. All this is possible, I showed you at scale, with very cost-effective materials. You don't want to be replacing systematically your anode, your container, or your cathode. All right, so here it is. I'm going to skip ahead. That's a bit for the happy few. We work on a triangle since 1980, and then we say, you know, performance is what drives society, and then that's a tetrahedral, right? It's four corners. But then sustainability comes in, and then we're like, how do we make a four-corner thing with two things? So that goes back to the Greek, right? It's the god, it's the myth. How do you make it work? All right, so what do? We just try to contribute with modest contribution. The first one is trying to do at low temperature. The bottom right, the top right is a very high temperature, and the one in between is at middle range temperature. All right, all this makes sense. The first approach is to use low temperature. These are hematite particles, basically those material grinded to about 100 microns or 50 microns. The iron oxide goes to the negative electrode. It gets the electron. The iron is reduced to iron 0, and the oxygen is released as OH minus, and then you have oxygen on the other electrode. That's how you complete the reaction. It's a completely surprising thing. This should not happen. Like if you trust and if you follow the textbook about how fast can oxygen move in that thing at room temperature, oxygen will not move. It's going to take 10,000 hours to see any atom of oxygen moving in that system. So how is the oxygen coming out? By electrochemistry. This is an insulator. How can you do electrochemistry of an insulator? All right, so these are all things that we can study with electrochemistry, but basically we see that there is actually penetration deep inside the particle. Here is the original oxide, the metal is here. But if you look even more carefully with the tools of microscopy, XRD, you know, all the characterization tools that you can only learn in material science and engineering, you can actually see that there is a small gap between the hematite and the iron, and actually there is perhaps a dissolution phenomena that accelerate the conversion and allow reaction. Now, this is important because it brought to the world the first iron-making cell in the 20th century that was CO2-free. And here is the pilot. You can see the hematite slurry on the top. And recently, they've been able to reach about the size of that table at scale, and they are projecting a pilot, industrial pilot, in the next couple of years. Now, this is making plates. So these plates are going to have to be remelted, which means you need an electric arc furnace. An electric arc furnace emits about 300 kilograms of CO2 per ton of steel. So even if you say electric arc furnace is clean, actually you don't eliminate CO2 emission by just using an electric arc furnace. So here is the second approach, very high temperature, and yes, it says oxide, so it stays that thing, but it's going to be molten. So that's going to be hard for me to show you, and you're not going to believe it. So we made a setup here at MIT, which is containerless. In that case, we're studying a molten aluminum oxide, just for the sake of clarity. We are basically inserting 3 electrodes, only 2 of them really matter. Here is the anode that is here, and if you watch the movie, you can see the oxygen that is coming out from molten aluminum oxide, and on the cathode, you make liquid aluminum, and on the other electrode, you make oxygen gas. You can see a bubble that got trapped here, and you can see others that are coming out. So this is an example where, again, aluminum oxide is a typical insulator. If you say to your chemistry teacher, oh, I'm doing electrolysis of aluminum oxide, I think I saw it online, by the way. This was a real question of a chemistry teacher for undergraduates, right? So you want to do electrolysis of aluminum oxide, how would you do it? Right? It's a good point. Well, here is how we do it. We melt it, and suddenly the ions can move, and now you can do electrochemistry. All right, so here it is. To do with liquid iron and oxygen, however, you need to inspire from aluminum industry, and here Professor Sadoway championed that technology for a very long time, really inspired by aluminum electrolysis, but at a temperature way higher. Here what we need to remember is these high temperatures are achieved because the current is flowing. You need to think about this like an electrical resistance. You have a finite resistance that is higher here than in the anode or the cathode, and that's how the heat is generated, and at the same time, the electrochemical reaction happens so that you can make the metal. Now, the problem is you have to make this carbon-free, so you need to find materials to do the anode. Here is a movie of the anode generation that was done at MIT. Here is a crucible. Here is the anode at the top, and if you look carefully in that region, you can see oxygen gas from molten iron oxide, molten oxide electrolysis at a temperature of 1565 degrees Celsius. Now, the anode was made of chromium. Here it is, before and after. Yes, it's pretty. I don't know, I find it pretty both ways, but you'll tell me. The current density is twice the one of aluminum production, so we're on the right track. And so much that at some point you can even study the stability of the alloy, and you can appeal to all the suite of now oxide and high temperature corrosion and oxidation protection, which is so important for many applications. You know, you've heard about the rocket and all these things. These are all possible because of controlling of the oxidation behavior at high temperature of materials, and that is what we do in the department. So speaking about the department, in 2013, Professor Sadoway here in the middle, myself and Jim Yurko recognized that this could no longer be done in these small furnaces. We have to go to self-heating, and that's why we created the corporation, Boston Electrometallurgical Corporation, with the support of the investor Ingo Wende. In 2023, you can read probably a lot about this. The company is named now Boston Metal, and you can see the reactor made by alumni from the department in the very early days of the company. All right, the last one, which is going on right now in my laboratory and which might interest you, is the idea of moving away from oxide. I think there are good technological solutions for iron oxide electrolysis. I showed you two. They are both going to industrial scale. At some point it will work, it will do what it can. But there's an interesting aspect of going to sulfides, because I will show you maybe at the end of this lecture, if you come forward, I have some samples to show you of anything you would like. Literally, I'm like a merchant bringing stuff. So feel free to come by, and I think we have half an hour more that I can discuss privately with you. Anyway, so pyrites, right, the point is pyrites, right? You may know that on Earth you have oxides and you have sulfides. These are basically the two things you need to know about. The rest, whoop. Lithium carbonate, whoop. Carbonate. You can get lithium from oxide, right? Okay, so why would you go anyway? Iron sulfide, so pyrite, a version of pyrite. If you could do that, there's no oxygen in the system. You see that? No more CO2 emission, no more problem. Well, there are other problems, but you have to deal with them. So the point is you can be at lower temperature, and maybe if you remember your chemistry, there's only 2 electrons in FES, right? S2 minus, Fe2 plus. So now I'm paying only 2 electrons where everybody pays 3 electrons. And furthermore, the binding energy between sulfur and iron is way lower than iron and oxygen, which means you need less energy no matter what. And what is very exciting, at least to me, is the fact that potentially you could make a liquid iron product, which we call hot metal in the industry, that could be directly fed to the continuous casting and the basic oxygen furnace. So we have a much smoother integration of this. And again, I think now you're familiar with that setup. That's the second time. Here is the containerless method with the molten sulfide here. The anode is at the top, made of graphite, bottom graphite. And then if you wait long enough, here is the electrolyte. If you wait long enough in that region, I think you will see movement, which is always exciting when you do electrolysis, right? If there's no movement, something is wrong. So here it is. Here is the sulfur that is bubbling out from that molten electrolyte. And it's really remarkable, at least at that scale. We've been able to basically measure the amount of sulfur that left the system, and it's exactly Faraday's law. And within 1 or 2%, it's basically Faraday's law in action in an electrolyte based on sulfur. Okay, at some point, this is a very small setup, right? So at some point, the sulfur doesn't have time enough to leave, and now it becomes a bit bubbly and foamy, and now the steel makers come and say, oh, you can't do anything with this because it's small, okay? That's why you don't do anything. Here it is, scale up at 300 grams per hour. We did that actually with copper. Here is an example of the refractory material. This is the size, this is about 7 centimeters, and here is the hot metal at the bottom and the electrolyte here. Now, finally, since I didn't know, we could have done a live experiment, right? There's current and voltage. Now, the current doesn't go high enough because it's 30 amps, and this is actually 40 amps. Well, we beat the room. So here is 40 amps running of current, and then here is your cell voltage, which keeps oscillating because you have this sulfur that keeps arriving, leaving the system, arriving, leaving the system, so your conductivity changes drastically. All right, I see we're getting close. I want you to go home, but before that, I want you to remember that there is a saying in metallurgy that says that the metallurgist is a jack of all trades and a master of few. And I know it sounds scary, but it's actually very important, right? Because if you think about your long life of professional life, you're going to have to be able to adapt to any changes that could happen. And we hear about it now in computers and AI, right? Like basically, think about it. Think twice about it. 3 times about it, right? Because what you're learning here, I just told you, it's going to be true on Mars, right? So when everybody goes to Mars, you'll be like, hey, I know exactly what's going on here. That may not be the case with your last code. Anyway, it's the home of the understanding of material. So if you have interest in how building blocks come together and give you condensed matter, this is the right place to be. And I think I convinced you that the modern infrastructure relies on this. Now, I will say, and I think people can attest on this, this is a very rigorous curriculum. This is not an easy one, but it's broad. Okay, in the first year, it's not as broad as you would like. That's okay. It's going to get broader after, and I showed you how broad it can be, and I think this is quite inspiring because you can also get very important job in the industry. I showed you Mr. Yurko, right? The guy on the left. So this person now works at the largest electronic company in California, in Cupertino, right? Okay, so he's in charge of 100 people who are all material scientists and engineers who are working with him to solve the next generation of problems and develop those materials sustainably. And that was possible for him thanks to his diploma in material science and engineering. So there's a lot of jobs out there that are real, and you can even do a successful research career, of course, if that's interesting. And if ultimately this is not sufficient to convince you, the last point, right? Your only connection to the universe, your only connections to your past fellows humans is going to be through the materials. There's no wave, none of that. It's all about atoms and electrons. So with this, I dedicate this talk to all students and your universal mind. That will be the end.
Thank you, Antoine. Questions? I'll run around with the microphone, please.
Thanks for the question, for the talk. And I have 2 questions. First, what is the impact of purifying the process, like mechanical and physical treatment, before having hematides for this process, electrochemical process? And my second question is a little bit similar with what you're doing here for iron production. What about nickel, for example, nickel and cobalt, other elements, because they are also found as oxide and sulfides as well in the nature? Thank you.
Yeah, so the first point is related to the ore, right? The ore is basically not always pure, like I said. And the question is, what's the tolerance of these new processes to impurities? Well, I mean, clearly, you need to study impurities, you need to reach a scale where they start to matter. So that's the first point. Some of those technologies are still not yet at a scale where you could study the accumulation of impurities. What I mean by that is iron ore, certain iron ore in particular, don't have that many impurities that are detrimental. Like alumina, silica is probably easy to handle. Now, phosphorus might be a different question. The second question was, could you apply this to other form of oxide? Yes, definitely. And as a matter of fact, most of these new ideas, even though everybody's aiming for iron, on the way to iron, people are also looking, could it be used for nickel or cobalt or manganese? So it's a fully integrative approach. And I focused here on iron and steel just to condense it. But this is very important because the laws that you will be learning with the material science engineering will apply as well to a nickel oxide, a cobalt sulfide, and so on and so forth. So this is completely integrated in what we do.
Now, I should have mentioned before we started losing audience, immediately following, there's a reception just down the hall in 6104. So please do stick around. More questions, please.
I can also speak.
It's for the, yeah.
Yeah. So thank you for the talk. I have also like two little questions. You mentioned about the electric arc furnace and how it still has like about 30% or 30 some unit of CO2 emissions per ton of steel. And if you had like a completely green energy source, like I'm curious, where does that come from? And the other question about pyrite, like how much do we have of iron sulfide, and could we actually do like a significant decrease of using oxygen with this mineral?
Yeah, this is very important. So the electric arc furnace works with graphite electrodes. And the problem is whatever you're feeding here has some oxygen with it. And it's going to end up burning some of the graphite as you're doing an AC arc. Because you never can really completely insulate your large-scale furnace from any makeup air that will happen. So for example, I don't know if you've seen this video, I encourage you to look at them, they are wonderful. On YouTube, where you feed the scrap, the thing is already hot. And guess what? When you feed scrap, you feed oxygen, oxide, and all that stuff, and the graphite is going to be there to remove that, and that's where we end up with emissions. The second question about pyrite, well, this is a good question. I mean, pyrite has historically been mined, and we stopped mining it because of acid generation, and also the fact that sulfuric acid was mined to make sulfuric acid, to be very specific, right? So we oxidize the iron oxide, and then we leave sulfuric acid behind. This was dismissed by the oil and gas industry because the oil and gas industry today is the largest generator of sulfur from the H2S that comes from the oil and gas. So suddenly we stopped looking at pyrite because there was sulfuric acid from oil and gas. So the clear message is I don't think we are saying we're going to substitute the 4 billion tons of iron oxide with iron sulfide. But I think in certain context and scenario, it is worth looking at. In particular, because pyrite is often a byproduct of copper extraction, and therefore we would like to do something else than just letting leach to acid.
So I have two questions as well. So how does this like electrochemical method like compare economically with like direct reduced iron, as well as like maybe on the carbon dioxide emissions? And my second question is, how applicable is this system to more complex like systems of ores like arsenopyrite or like chalcopyrite?
Yes, so the first question, I don't know if you heard, is about the cost, comparing the cost of making, I'm going to simplify, making hydrogen versus making directly electrons. Well, the answer is that hydrogen by electrochemistry is very expensive. And if we are able to follow the metrics that I put forward, right, improving the current density and decreasing the energy consumption, then definitely if your electricity is carbon-free without emissions, then definitely this is the route that will decarbonize iron and steel production. Because that's where, when you ask the second question, where are the emissions coming from? They are coming from how you make electricity. The idea here is to have no reacting carbon in that system that could lead oxygen. I forgot about your second question. It was about... Yes, arsenopyrite, yeah. So this is an important thing. Well, everybody's familiar with arsenopyrite. The name says it, right? It's arsenic and pyrite. So you decide what's your poison. Is it sulfur or arsenic? Go back to the Greek. we are looking at methods where we can selectively remove the arsenic from the system. We call that sulfidation. It happens that if you are at high enough temperature, you can actually inject sulfur, and thermodynamically the sulfur will kick out the arsenic, and the arsenic will come out as a mixed compound arsenic sulfide, which then you can condensate and you can leave it quiet back to the mine. So this is long term, but we are thinking about those questions, how we can accommodate the impurities that might be coming with pyrites.
All right, I want to make sure folks have time to join us in the reception, and also, of course, to come view Professor Antoine Allannore's little peddler cart up front. So thank you, Antoine.
All right, thank you.